Good morning. Miss Rydell has come to say hello. And with that, we're going to go ahead and jump into 7.6, the fundamental trig identities. So yesterday we talked about how we talked about sine, cosine, tangent, secant, cosecant, cotangent, and you practiced using them on the unit circle. Today we're going to discuss more of those patterns, and I want to begin by discussing some of the patterns that we've already talked about, both in class and yesterday. For example, we learned that if we took a string, I'm going to draw a pretty poor unit circle here, but if we took a string and we wrapped it around the unit circle as a circumference, and then we laid that string out, that string was 3.14159 units long. And we also learned that if you took a string and if we took, let's see, if you took the length of this line here and you wrapped it around the unit circle, we did that 1 time, 2 times, 3 times, and then there was just a little bit left over. And again, that number 3.14159 came around. We also talked about how to convert from radians to degrees, and we learned that 1 degree on the unit circle is pi over 180. And we talked about where degrees came from, and we talked about where radians came from. And so today we're going to explore those relationships a little bit more. We're going to talk about the patterns on the unit circle that are far from coincidental. We talked about at the very beginning of trig how trig kind of is more than any other math. It shows us how the universe ticks, and we're going to see some more of that today. So I'm going to begin with some stuff that we have to understand before we get into today. And as usual, math is not necessarily working with numbers, but it's learning the language. So you're going to see a lot of something like this today. Sine squared of theta. Well, let's try that again. Sine squared of theta, much better, and cosine squared of theta. You need to learn how to rewrite those. So when they're saying sine squared of theta, we're squaring sine, we're squaring cosine. So to evaluate it, it's a lot easier to just put sine of theta in brackets and square the whole thing. It's a lot easier to take cosine of theta in brackets and square the whole thing. All right? So let's do an example here. If we know that sine of 2 pi over 3 equals root 3 over 2, then what is sine squared of 2 pi over 3? This is going to be our first example, all right? Well, we know that sine squared of 2 pi over 3 can be rewritten as sine of 2 pi over 3 squared. We square the whole thing. We know that sine 2 pi over 3 is root 3 over 2, right? They told us right there. So it's just going to be root 3 over 2 squared. Root 3 squared is going to be 3, and 2 squared is 4. So anytime you're having to evaluate sine squared or cosine squared or even tangent or secant squared, that's how we're going to do it. So that's the first thing that we need to know about today. Now, we get a different color here. First thing I'm going to do is I'm going to draw the equation for the unit circle. So the equation for the unit circle. that the equation of a circle, and this goes all the way back to chapter 1, is x minus h squared plus y minus k squared equals r squared, where h and k are the center point and r equals the radius. Well, the unit circle is a circle that's centered at 0, 0, and it's got a radius of 1. So if that is our circle, it's a circle that's centered at the origin, 0, 0, and it's got a radius of 1, then our formula is x minus 0 squared plus y minus 0 squared equals 1 squared. And that simplifies to x squared plus y squared equals 1. So this, again, is the equation for the unit circle. Now, I want to look at something else. Remember yesterday, we talked about the 30-degree triangle on the unit circle, right? How it kind of looks like that. What I'm going to do is I'm going to pull out that triangle. And you remember that all of these triangles, when we drew our unit circle, all of them had a hypotenuse of 1. And this line here was on the x-axis, right? X-axis up here. So we're going to call that x. And this line here is the y, is on the y, so we're going to call that y. It goes up, the x goes over, the y goes up. So if I were to write the equation for this, or if I were to use Pythagoras' theorem on this triangle, the formula would be x squared plus y squared equals 1 squared, or x squared plus y squared equals 1. Now, where have we seen that before? Right here. They're the same thing, right? And hopefully, if you're a nerd like me, you think that that's kind of cool. But even if you're not a nerd, it's still pretty interesting that we took two completely different things, right? The equation for a circle and triangles on the unit circle, and we ended up with the same equation. We ended up with this x squared plus y squared equals 1. Trig is all about patterns, all right? And so this equation, x squared plus y squared equals 1, is going to be so important that we're going to call it a fundamental trig identity. It's a fundamental trig identity. So, x squared plus y squared equals 1. And you remember yesterday we learned that x corresponds with all of the cosine values on a unit circle, and y corresponds with all the sine values on a unit circle. So we can rewrite this. X, instead of x, is going to be cosine of theta squared plus sine of theta squared, put those in brackets, equals 1. And because you're going to see it like this, I'm going to rewrite it into the terms that they usually use. So it's going to be cosine squared of theta plus sine squared of theta equals 1. That is the most important one. I'm going to give you two others because you're going to see them a lot and you're still going to need to use them. But this first one that we just did, that's the big one. So the second one is 1 plus cotangent squared theta equals cosecant squared theta, and 1 plus tangent squared theta equals secant squared theta. So I'm boxing these important ones. You should know those guys because we're going to use them quite a bit. And the most important one is that guy right there. So what do we do with these? How are we going to use them? Let's take a look at an example. If sine of theta equals 1/3 and cosine of theta is less than 0, find cosine of theta. So first thing I want to do is I want to determine what quadrant we're in. I want to determine what quadrant we're in on the unit circle. And I'll show you why that's important here in a second. Well, sine is 1/3. They tell us sine of theta is 1/3. So that means that sine is positive. All right, that means our y value, right? Sine is y. Our y value is positive. And it says cosine of theta is less than 0. So that means that cosine is negative. So, and cosines are the x values. So where is y positive and cosine negative? This is going to happen in the second quadrant. All right, now let's talk about what this actually looks like. We've got a triangle on the unit circle, guys. We've got some triangle on the unit circle, and can I get a black? Yeah, I can't. Sweet. All right, we got some triangle on the unit circle. It's gonna look like this. And there's theta. Sorry, I know that drawing's crappy, but I can only do so much. And we know the ratio, we know the proportions of the side. Remember, sine is opposite over hypotenuse. So the opposite side, the opposite from that angle is going to be 1. And the hypotenuse is going to be 3. Now, wait a minute, you might be saying. I thought that the radius, or that the lines extending from the origin to the circle are always 1 on a unit circle. And that's true. We're not actually saying that this side here is 1 and that this side here is 3. We're just saying that that's the ratio. That's how they're related. It could be anything, but when I simplify the relationship of opposite over hypotenuse, it's 1/3. All right? Shorten that up. You could just assume that the unit circle can expand and contract. So right now we have a hypotenuse of 3 and the opposite side is 1. So we can use the fundamental trig identities to solve this. We can use the fundamental trig identities. So we've got sine squared theta plus cosine squared theta equals 1. We know what sine of theta is. It's 1/3. So 1/3 squared plus cosine squared theta equals 1. Square 1/3, I'm going to get 1/9 plus cosine squared of theta equals 1. I'm going to subtract 1/9 from both sides. So I get cosine squared of theta equals 1 minus 1/9. So we can rewrite 1 as 9/9 minus 1/9. And that's going to give me 8/9. So cosine squared of theta equals 8/9. Now remember, we're looking for cosine theta, not cosine squared. So if I want to get rid of the squared, I have to take the square root of both sides. I'm going to erase this stuff over here so I have a little bit more room. So that's going to give me cosine of theta equals, and when we take the radical of a fraction, the square root of a fraction, we can take the square root of the top and the square root of the bottom. So cosine of theta is going to equal, 8 simplifies to, if we break the radicals out of jail, remember how to do that. Radical 8 simplifies to 2√2, radical 9 simplifies to 3. So we have our answer. The reason that we look for the quadrant, right, up here, the reason that we look for the quadrant first is because in the second quadrant, cosine is negative. So we have to make our answer negative. Cosine of theta is actually going to be negative 2√2/3. So that's why we always start with which quadrant am I in, because I always need to go back and check my answer and make sure that I'm right. Okay. Next example. If I can get there. There we go. All right. If cosine of theta equals 3/5, and this is supposed to be degrees, 270 degrees is less than theta, and theta is less than 360 degrees, find sine. Find sine. All right. So remember, we look for the quadrant first. Quadrant first. Let's do green. All right. So what quadrant are we in? Well, cosine is positive, and it says that we're between 270 and 360 degrees. So if I look at my unit circle, what quadrant is between 270 and 360? It's the fourth quadrant. It's the fourth quadrant, which means that sine, the y value, is negative. I would encourage you to pause the video now and try to work this out yourself. Okay, so either you worked it out and you want to check your work, or you're going to continue to take notes with me. Either one is fine. But let's go ahead and begin. So we've got our trig identity, cosine of theta, cosine squared of theta, excuse me, plus sine squared of theta equals 1. I know cosine, so I've got 3/5 squared plus sine squared of theta equals 1. 3/5 squared is going to be 9 over 25 plus sine squared of theta equals 1. Subtract 9 over 25 from both sides. I'm going to have sine squared of theta equals, I'm going to go ahead and change 1 to 25 over 25 minus 9 over 25. So sine squared of theta, 25 minus 9 is going to be 16 over 25. Take the square root of both. I'm going to get sine of theta equals square root of 16 is 4. Square root of 25 is 5. So sine of theta is 4/5. And remember, we're in the fourth quadrant, so I have to make my answer negative. It won't always change, but you do want to check that. Okay, so the most important takeaway from today is A, knowing what the fundamental trig identity is. B, knowing where it came from. Remember the equation for the unit circle and the triangle on the unit circle itself. And C, how to use it to solve for some of these unknown quantities.